Welcome to the series of e-learning modules on moment generating functions or MGF, its uses, properties and limitations. Here we have also proved the uniqueness of MGF, and using MGF we have obtained cumulant generating function and hence cumulants. At the end of this session, you will be able to understand about moment generating function, understand the uses of moment generating functions, describe the properties of moment generating functions, describe the limitations of moment generating functions, explain uniqueness theorem and obtain moments from cumulant generating functions. Introduction. In probability theory and statistics, the moment generating function of a random variable is an alternative specification of its probability distribution. Thus, it provides the basis of an alternative route to analytical results compared with working directly with probability density functions or cumulative distribution functions. There are particularly simple results for the moment generating functions of distributions defined by the weighted sums of random variables. Note, however, that not all random variables have moment generating functions. In addition to univariate distributions, moment generating functions can be defined for vector or matrix valued random variables and can be even extended to more general cases. Now let us discuss the usefulness of moment generating function. Moment generating function is useful in many ways. A. They provide an easy way of calculating the moments of a distribution. B. They provide some powerful tools for addressing certain counting and combinatorial problems. They provide an easy way of characterizing the distribution of the sum of independent random variables. They provide tools for dealing with the distribution of the sum of a random number of independent random variables. They play a central role in the study of branching processes. They play a key role in large deviations theory, that is, in studying the asymptotics of tail probabilities of the form P of x is greater than is equal to C, when C is a large number. They provide a bridge between complex analysis and probability, so that complex analysis method can be brought to bear on probability problems. They provide powerful tools for proving limit theorems such as laws of large numbers and the central limit theorem. The moment generating function or MGF of a random variable x about origin having the probability density function f of x is given by m x of t is equal to expectation of e to the power tx is equal to integral of e to the power tx into f of x dx. The integration being extended to the entire range of x, t being the real parameter, and it is being assumed that the right hand side of the moment generating function is absolutely convergent for some positive number h, such that minus h less than t less than h. Thus, mx of t is equal to expectation of e to the power tx is equal to expectation of 1 plus t into x plus t square into x square divided by 2 factorial plus etc. plus t to the power rx to the power r divided by r factorial plus etc. is equal to 1 plus t into expectation of x plus t square by 2 factorial into expectation of x square plus and so on till plus t to the power r divided by r factorial into expectation of x to the power r plus etc. is equal 1 plus to q plus t into mu 1 dash plus t square by 2 factorial into mu 2 dash plus etc. plus t to the power r by r factorial into mu r dash plus etc. is equal to summation over r is equal to 0 to infinity t to the power r divided by r factorial into mu r dash, where mu r dash is equal to integral over x to the power r into f of x dx is the rth moment of x about origin. Thus, the coefficient of t to the power r divided by r factorial in mx of t gives mu r dash about origin. Since mx of t generates moments, it is known as the moment generating function. Given the moment generating function, we can also find moments by differentiating it with respect of t, r times and then putting t is equal to 0. That is, rth derivative d power r dt power r mx of t at t is equal to 0. This is equal to mu r dash divided by r factorial into r factorial plus mu r plus 1 dash into t plus mu r plus 2 dash into t square divided by 2 factorial plus etc. at t is equal to 0. This implies mu r dash is equal to d to the power r by dt power r. Mx of t at t is equal to 0. In general, the moment generating function x about the point x is equal to a is defined as mx of t about x is equal to a. This is equal to expectation of e to the power t into x minus a is equal to expectation of 1 plus t into x minus a plus t square into x minus a the whole square divided by 2 factorial plus etc. plus t to the power r into x minus a power r divided by r factorial plus and so on is equal to 1 plus t into mu 1 dash plus t square divided by 2 factorial into mu 2 dash plus etc. till plus t power r divided by r factorial into mu r dash plus and so on, where mu r dash is equal to expectation of x minus a whole power r is the rth moment about the point x is equal to a. Now let us discuss some of the limitations of moment generating functions. Moment generating function suffers from some drawbacks which have restricted its use in statistics. Below are some of the deficiencies of moment generating function. We have discussed these in detail in the first semester. A random variable x may have no moments although its MGF exists. A random variable x can have moment generating function and some or all moments, yet the moment generating function does not generate the moments. A random variable x can have all or some moments, but MGF does not exist except perhaps at one point. Consider the following illustration. Show that for the following distribution with probability density function f of x is equal to theta into a power theta divided by x power theta plus 1, where x is greater than or equal to a and theta is greater than 1. The moments of all order exist, but moment generating function does not exist. Proof. Now consider rth raw moment. Mu r dash is equal to expectation of x to the power r is equal to theta into a to the power theta into integral over a to infinity x power r minus theta minus 1 dx. This is equal to theta into a power theta into x power r minus theta divided by r minus theta. Ranges from a to infinity. This is equal to theta into a to the power r divided by theta minus r, where theta is greater than r. Hence, rth raw moment exists. Now let us consider the moment generating function of the given distribution. Mx of t is equal to expectation of e power t x is equal to theta into a power theta into e power t x divided by x power theta plus 1 dx, which does not exist. Since e power t into x dominates x power theta plus 1 and e power t into x divided by x power theta plus 1 tends to infinity, and hence the integral is not convergent. That is, moment generating function for the given distribution does not exist. Now let us discuss some of the properties of moment generating function which holds good for continuous as well as discrete random variables. The first property is stated as follows. mc into x of t is equal to mx of c into t, c being a constant. Let us prove this as follows. By definition, left hand side is equal to mc into x of t is equal to expectation of e to the power t into c into x is equal to expectation of e power t into c into x is equal to mx of c into t, which is equal to the right hand side. Hence, the proof. Second property is given as follows. The moment generating function of the sum of the independent random variables is equal to the product of their respective moment generating functions. Symbolically, if x1, x2, x3, etc. till xn are independent random variables, then the moment generating function of their sum x1 plus x2 plus x3 and so on till plus xn is given by mx1 plus x2 plus etc. till plus xn of t is equal to mx1 of t into mx2 of t into etc. till into mxn of t. Proof. By definition, mx1 plus x2 plus and so on till plus xn of t is equal to expectation of e power t into x1 plus x2 plus and so on till plus xn is equal to expectation of e to the power t into x1 plus t into x2 plus etc. plus t into xn is equal to expectation of e to the power t into x1 into expectation of e power t into x2 into etc. into expectation of e power t into xn is equal to mx1 of t into mx2 of t into etc. till mxn of t. The third property is about the effect of change of origin and scale on moment generating function. Let us transform x to the new variable u by changing both the origin and scale in x as follows. U is equal to x minus a divided by h, where a and h are constants. Moment generating function of u about origin is given by mu of t is equal to expectation of e to the power t into u is equal to expectation of exponential of t into x minus a divided by h. This is equal to expectation of e to the power t into x divided by h into e to the power minus a into t divided by h is equal to e power minus a into t divided by h into expectation of e power t into x divided by h. This is equal to e to the power minus a into t divided by h into expectation of e power x into t by h is equal to e power minus a into t divided by h into mu of t by h, where mx of t is the moment generating function of x about origin. In particular, if we take a is equal to expectation of x is equal to mu and h is equal to sigma x is equal to sigma, then u is equal to x minus expectation of x divided by sigma x is equal to x minus mu divided by sigma is equal to z is known as a standard variate. Thus, moment generating function of a standard variate z is given by mz of t is equal to e power minus mu into t divided by sigma into mx of t divided by sigma. From the above, note that expectation of z is equal to expectation of x minus mu divided by sigma is equal to 1 by sigma into expectation of x minus mu. This is equal to 1 by sigma into expectation of x minus mu. This is equal to 1 divided by sigma into mu minus mu, which is equal to 0. And variance of z is equal to variance of x minus mu divided by sigma is equal to 1 by sigma square into variance of x minus mu is equal to 1 divided by sigma square into variance of x is equal to 1 divided by sigma square into sigma square, which is equal to 1. Therefore, expectation of z is equal to 0 and variance of z is equal to 1. That is, mean and variance of a standard variate are 0 and 1 respectively. Now let us consider the uniqueness theorem of moment generating function. The moment generating function of a distribution, if it exists, uniquely determines the distribution. This implies that corresponding to a given probability distribution, there is only one moment generating function, provided it exists, and corresponding to given moment generating function, there is only one probability distribution. Hence, mx of t is equal to my of t, implies x and y are identically distributed. Proof: if x and y are two random variables with probability density functions f of x and f of y respectively, let moment generating function of two distributions be given by mx of t and my of t respectively. We need to prove that if mx of t is equal to my of t, then f of x is equal to f of y. We know that moment generating function of x and y are given by m of t is equal to expectation of e to the power t into x is equal to integral over x e to the power t into x f of x dx, and my of t is equal to expectation of e to the power t into y is equal to integral over y e power t into y f of y dy. If mx of t is equal to my of t, it implies integral over x e power t into x f of x dx is equal to integral over y e power t into y f of y dy, which implies f of x is equal to f of y. That is, x and y are identically distributed. Cumulant generating function of the distribution is obtained from moment generating function and is denoted by kx of t and is given by kx of t is equal to log mx of t to the base e, provided the right hand side of the equation can be expanded as a convergent series in powers of t. Thus, kx of t is equal to k1 into y plus k2 into t square divided by 2 factorial plus and so on till plus kr into t to the power r divided by r factorial plus and so on is equal to log mx of t to the base e. This is equal to log mu 1 dash into t plus mu 2 dash into t square divided by 2 factorial plus etc. till plus mu r dash into t power r divided by r factorial plus etc. where kr is equal to coefficient of t to the power r divided by r factorial in kx of t is called rth cumulant. Hence, k1 into t plus k2 into t square divided by 2 factorial plus k3 into t cube by 3 factorial plus k4 into t to the power 4 divided by 4 factorial plus and so on is equal to mu 1 dash into t plus mu 2 dash into t square divided by 2 factorial plus mu 3 dash into t cube divided by 3 factorial plus mu 4 dash into t to the power 4 divided by 4 factorial minus half into mu 1 dash into t plus mu 2 dash into t square divided by 2 factorial plus mu 3 dash into t cube divided by 3 factorial plus mu 4 dash into t power 4 divided by 4 factorial plus 1 divided by 3 into mu 1 dash into t plus mu 2 dash into t square divided by 2 factorial plus mu 3 dash into t cube divided by 3 factorial plus mu 4 dash into t to the power 4 divided by 4 factorial minus 1 divided by 4 into mu 1 dash into t plus mu 2 dash into t square divided by 2 factorial plus mu 3 dash into t cube divided by 3 factorial plus mu 4 dash into t to the power 4 divided by 4 factorial plus and so on. Comparing the powers of t on both sides, we get the relationship between the moments and cumulants. Hence, we have k1 is equal to mu 1 dash is equal to mean. k2 divided by 2 factorial is equal to mu 2 dash divided by 2 factorial plus mu 1 dash square divided by 2 factorial. This implies k2 is equal to mu 2 dash plus mu 1 dash square is equal to mu 2. k3 divided by 3 factorial is equal to mu 3 dash divided by 3 factorial minus half into mu 1 dash into mu 2 dash divided by 2 factorial plus mu 1 dash cube divided by 3, which implies k3 is equal to mu 3 dash minus 3 into mu 2 dash into mu 1 dash plus 2 into mu 1 dash cube is equal to mu 3. Also, k4 divided by 4 factorial is equal to mu 4 dash divided by 4 minus half into mu 2 dash square divided by 4 plus 2 into mu 1 dash into mu 3 dash divided by 3 factorial plus 1 divided by 3 into 3 into mu 1 dash square into mu 2 dash divided by 2 factorial plus mu 1 dash to the power 4 divided by 4. On simplification, we get k4 is equal to mu 4 dash minus 4 into mu 3 dash into mu 1 dash plus 6 into mu 2 dash into mu 1 dash square minus 3 into mu 1 dash to the power 4 minus 3 into mu 2 dash minus mu 1 dash square the whole square. Hence, K4 is equal to mu 4 minus 3K2 square, implies mu 4 is equal to K4 into 3K2 square. Here's a summary of our learning in this session, where we have understood about moment generating functions, understood the uses of moment generating functions, explain the properties and limitations of moment generating functions, understood the uniqueness theorem, understood how to obtain moments from cumulant generating functions.